Great. Thank you very much for the introduction. Thank you for having me here today. I'm pretty excited for being in a new role and being able to address to you today what I'm up to. So again, our business model, we build this IP, we license it to silicon partners. Here you see the Cavium, Marvell, ThunderX, the Fujitsu AFX64, A64FX, and then the Huawei Kangping 920, I think it's called. There's a bunch more here. On the server side, there's a bunch more. There's Ampere is one that comes to mind. AWS just did a processor that I'll have a slide on a little bit later. In all these cases, that separation of them taking a license allows them to go off and do their own thing. So in some of these instances, we don't have absolute understanding of what the silicon partner is doing because they're adding their own logic to the side of the base technology that we've licensed to them. They're able to come back and ask for our help, and we do provide that help to get them over the hump and into real silicon, but it's not a requirement. So when a partner licenses the IP, they can run off and build what they want. So we don't have full clarity on everything that's going on there, nor do we share roadmaps. So I can't tell you what the Marvell roadmap is for the ThunderX processor. That's a NDA discussion between you and Marvell, similar with other silicon partners. So further down the road, there is a platform integrator. In the case of the ThunderX2 processor, Hewlett-Packard, Atos, Bull, and Cray are all in the market with these devices. So they've designed motherboards and logic around the ThunderX processor and are in the market bidding those designs. Downstream from there are the actual deployments. So you can see that this is several layers of interactions, and it takes a whole lot of discussion and helping one another succeed in this market. It's a nascent market at this point. ARM is by no way threatening the incumbents at this point. We believe the roadmaps are super strong. The software quality is very high and coming along fast. We have lots of reasons to be optimistic about where this goes. At SC, one example came out, the Astro machine, which is a HPE machine installed at the Sandia National Lab. 2,500 Apollo 70 nodes, coming in at, I believe, number 203 or so on the top 500 list. And I've been involved in many HPC installations that are this size or larger. And I can say from a vantage point of observing this that it was one of the easier installs that I've seen. The description from the application software people is a little bit hard to believe, but the stories you get in these sites is that the software compiles and runs. Now that's separate from running in an optimal manner, but it compiles and runs is not a statement I would make about any of the Blue Gene software that we had to get going on that system when it was first coming out, or any of the previous killer micro machines that we worked on. And we attribute this to the Alinea software group, which was an independent tools group, compiler group that ARM acquired about 2 years ago. This group, which is now wholly owned and internal to ARM, is multi-platform support for performance tools, debugging tools, and compilers. So for years, they've been supporting that software on x86, on Power, on different platforms. And so when you think of it, an application that would compile through this tool set and run on x86 has a pretty good chance of compiling with a different backend for ARM, and it's turning out that modulo the optimization passes that need to be done, that's really the case. There's a handful of other announcements. All of the vendors that I mentioned, Cray, Atos, Bull, and HPE, have installs at this point. The Cray system that is in Bristol had a very interesting paper about a year ago at the Cray user group where they showed the performance at par or above current generation Xeons. So the limited exposure that they've had to the system there says that it performs quite well. That system hunts today, the Thunder X2 with the Cray. I believe that system is a Mellanox interconnect on that. It's not a Cray interconnect. CEA has some, Los Alamos has some. Most of the labs have at least a partial rack of Thunder X2 that they're looking at, both in the US and in Europe. HPE stood up and donated systems to 3 different universities in the UK to try and kickstart the market and get some of the software going. The first meeting of that consortium, called the Catalyst, is happening this week in the UK, London, I guess. So we're going to hear from those installs and start seeing what performance they're eking out of the software ecosystem there. So that's another exciting activity. There is an announced project with the Los Alamos National Laboratory between Marvell and Los Alamos that is also very interesting. I invite you to go read the press release on that. These systems currently are lacking one specific feature that is widely talked about and hugely anticipated. And I am super excited to see how this Fujitsu hardware lands, because it has implemented the scalable vector extension instructions. So part of the ISA for the version 8 dot something of ARM is this SVE instruction, which is a variable length vector instruction. So it's from 256 to 2048 in width, and the hardware gets to decide what width they put down on the silicon, but the software doesn't need to change. You don't need to recompile your code to switch from one hardware base to the next. It hasn't been implemented in hardware up until now. The Fujitsu chip is the first one implemented in hardware, and I keep getting winks and nudges from Satoshi that it performs really well, but I haven't seen, other than what you've seen in his talk yesterday, I haven't seen the results myself. The fact that you're going to combine a 2x256 vector with a terabyte of memory bandwidth, I think should give you an indication that this thing is going to be super hot and will perform quite well on most applications. What's that? 2 times 512, sorry, yes, 2 times 512. And I didn't mean hot in the thermal sense. I meant that in the performance sense. So a lot of what we pay attention to is the software, because really we look at this as enabling our partners to be able to be in the market. So we have the large team, the Alenia team, we have a whole software group stationed worldwide that interacts, and they do a whole lot of outreach and partnerships and helping get base level software, operating system software, message passing software. We have our fingers in the entire stack as best we can to try and make that software A, work on each of the platforms, and B, performant on the platforms. You'll see a whole lot of product names up there. We have recently announced Lustre in collaboration with my old team at WAM Cloud. There is Lustre support available on the client side. We're looking forward to working with them on the server side for that. GPFS is not yet in plan, but we're covering the technologies down to the individual level so that we can make as much as possible available to this community. It's important to underscore here that it's really a community activity. The folks at Red Hat did much of the work themselves to make Red Hat available on the ARM system. There's one individual there, John Masters, who, if you don't know who that is, you should do a search on that name and follow him on Twitter. He's quite prolific, very driven, and an interesting character, but he has himself led the Red Hat effort to support ARM, and now ARM is a tier 1 supported hardware platform for Red Hat. So lots of work going into the software tools and infrastructure there. But another set of activities that we've got going now are the open source applications. And to the best of my knowledge, all of these applications are running on ARM platforms at this point. And again, that's not to say that they're super optimized or beating the incumbent processor technology at every turn of the crank, but they're available and ready to be used by the community. There are a couple of cloud providers that are standing up hardware, so you'll be able to go out and rent ThunderX2 processors by the hour if you want to go play with this stuff. We have been putting up the infrastructure to rally the HPC community around a few URLs here. So these will give you access to what we're up to and real-time information on what the systems are doing. So I invite you to come participate in the software community. Now, I mentioned as I started that ARM's background is in IoT. One of the reasons that ARM is interested in high-performance computing is that we see a shift in the architecture of the internet. And I think the architecture of the internet and the nodes on the internet drive the commodity technologies at such a rate that we in high-performance computing need to pay attention to them. So I want to switch gears here a little bit and talk about preparing for the next wave of computing. The internet today basically exists to send photos of cats from YouTube to your phone, right? It's a gross simplification, but literally the bandwidth from the internet is pointed out from the data centers to your desktop, your laptop, your iPad, your phone, and video is the typical content or the heavy content that goes out. 150 exabytes a month today is going out that way. We think that that flow of data is about to switch because of all of the edge devices, and remember, ARM is very big in the edge. We see what's going on there. We think that data flow is going to turn around. If you take, for example, 1 billion video devices, and these video devices are the devices that go in your phone, they go in your security camera, 1 billion of those, and by the way, there's over 1 billion iPhones in circulation, so 1 billion is not a big number. If you had 1 billion video devices trying to send data back upstream into the cloud, that would be 400 exabytes of data a month. I just said that the outbound data, which is what we're designed for, is 150 exabytes. So if these devices start to proliferate and the architecture doesn't change, we will break the internet backhaul. We're envisioning a time when we go from caching data going out to being unable to cache data coming in because it's all different. That would take and consume over 40 million servers, which is more than what the cloud providers have today. So clearly it's broken. We can't get from here to there, okay? There's a new group inside ARM called the Infrastructure Group, which is what I belong to. The Infrastructure Group in ARM is paying attention to everything in blue, everything to the left of the IoT devices, okay? We're paying attention to all the networking, we're paying attention to all the computing in the fog, which is the middle ground, and we're paying attention to everything in the data center. So sorry for a little bit of marketing here. We envision a future where there's 1 trillion edge devices. That's much more than the billion that I just talked about. In that environment, you have to be able to push compute out towards the edge. So we're talking about how to get the machine learning and recognition portions of workloads pushed all the way out into the edge devices, how to filter and process data at every step of the internet coming back, and how to only bring back the data that's critical to the workloads that you care about, okay? Today, ARM is the #1 market share holder for devices that I just told you we're starting to pay attention to. Because of all of the embedded ARM devices in all of the networking and storage, ARM actually has a very large market share in infrastructure. ARM has not been visible thus far because it's mostly embedded operations, and now we're just starting to look at servers. So from an HPC point of view, ARM is a newcomer because we're starting to help with our partners pay attention to servers, but ARM is sprinkled entirely throughout the network at a very large scale. There were 21 billion silicon devices shipped last year with ARM-based technology on them. There are about an order of magnitude more silicon wafers fabricated with ARM-based technology than with what we consider to be the market leader technology when we think about servers. All of the silicon providers are optimizing their processes for ARM-based designs because it is so prevalent throughout all of the designs going on. So ARM is not a slouch in this department. ARM is really a force to be dealt with here. Last fall, in addition to announcing our infrastructure group, we announced a new product line called Neoverse. You'll hear us use this in our marketing materials, and the way to think of that is it's everything to the left of the infrastructure. For high-performance computing, think of the servers, think of the interconnect. By the way, Mellanox is an ARM design, so when you think of the IB fabrics, ARM is already inside your supercomputer. We are building designs today that will scale from the edge to the core and licensing those designs to our partners. So the partners have the option of how many cores to put down, how much bandwidth to put on them, what the interconnect is on them. And we're paying attention all the way down to the cache lines, how they work, how big they are, all the gather-scatter units for vector instructions. It is highly likely that your cell phone will have a vector capability in an ARM processor very soon now. So the SVE instruction is going to go a long way. I spend a lot of time trying to figure out what the proper vector width is for machine learning algorithms, knowing that the HPC community would use as wide a vector as we would give you, and that we need to produce IP that is more broadly applicable than just the narrow focus of high-performance computing. We have a roadmap, the ARM Neoverse roadmap. The current instantiations of this, you'll notice, are 16 nanometer. We're taking a huge jump to 7, and we are promising, I think I have it in the next thing here. We don't. I believe the performance increment, this is on tape, so this is going to come back to bite me, but I believe there's a 30% performance promise annually throughout the different phases of our roadmap here. So we're already planning for 5 nanometer, and I don't know whether you disclosed what process technology you're using for the EPI. Did you disclose that? No? Okay. In this environment, we, again, are also giving our partners an ability to show up with their own notion of what the fabric might look like, how much I/O to put on it, what sort of HBM to put on it, what other sort of unique IP to bring to bear for that processor. And of course, this is wider than just high-performance computing. For this audience, you've heard from some already using it, but with Ampere and Huawei and various other partners, we work closely with those that want to work with us to help them enable this technology. So that's kind of the Neoverse hardware story. The software story is quite critical here. As I mentioned, with the number of wafers and the process technology and how much traction ARM has with the hardware, we predict and are seeing signs of, but we're looking for signs of, the software ecosystem shifting to ARM as well. When we announced the Neoverse ecosystem, these are the logos that jumped on board and said that we would come out with ARM and say that we're supporting your ARM processors in these environments. The bold prediction that I'm making here is that the common platform in 10 years will be an ARM platform, and the common software target will be an ARM-based target. That, to me, is a fundamental change and will enable HPC using these technologies. So we've built an environment where HPC now can build its own hardware and take advantage of the broader ecosystem software that today we're dragging along with our own efforts and sweat and blood of our community, but tomorrow that grows into all of the major cloud providers and the major silicon, or the major companies that can afford to do a $100 or $200 million project. So a broad endorsement of, effectively all of the Linux providers, the container providers, all the languages, all of this is going on now, targeted not at HPC specifically, but targeted at ARM-based processors. Just after SC last year, Amazon came out and announced a new project called Graviton, and it went live that same day, which is what Amazon typically does. You can now go and rent by the hour Amazon instances that are based on an ARM core. Now, these aren't high-performance computing cores. These are just ARM cores. They run some workloads 40% more efficiently when you take into account what you're paying for your hour of CPU time. Amazon has said there's a 40% efficiency gain in some of the workloads that they're tracking. The second thing they announced at their event was a kernel bypass messaging infrastructure. That's something that's near and dear to our hearts, but I don't know of anybody in an IT environment that pays attention to that level of message passing efficiency. The third thing they announced was Lustre support done by Amazon in the cloud. I'm happy that I don't have any insider knowledge here, so there's no way I can trip over myself, but all of this points in a direction that if there are subsequent processors from the Graviton family coming from AWS, they might be super interesting to this community down the road. That's an example of a non-silicon provider who can afford to build their own solutions, going out and building their own solutions. This is how we get performance scalability down the road. Take a look at the Turing acceptance talk by Hennessy and Patterson, and they talk about domain-specific logic being burned into hardware. That's the environment that we're providing. You can take your own domain-specific logic, start from an ARM-based core, put your own domain-specific logic on it, put as much I/O as you want on it, and then scale that up to whatever size you want. So it looks like I'm just about out of time. I will stop here. Thank you.